Hello and welcome to Math 275 Differential Equations here at Cañada College. My name is Lapuz. In this video we will do this problem. This is a second order non-homogeneous Cauchy Euler differential equation. And we know it's a Cauchy Euler differential equation because each of the derivatives of the unknown function is going to be multiplied by x to that same order derivative. So we have x squared times y double prime, x times y prime, etc. This is non-homogeneous because we have a right-hand side, and this is second order. So if you remember the whole process for this, our solution will be of the form y is equal to y sub c plus y sub p. Now from here we're going to branch off to do parts of this problem, and first we will find y sub c, and y sub c is the solution to the associated homogeneous differential equation. So that's general solution, and we will see that y sub p is going to be the particular solution. And that particular solution, well, we'll take a look at what that particular solution would look like. First, let's deal with the associated homogeneous differential equation. We have a 2x squared y double prime plus 5xy prime plus y is equal to 0. And if you remember, we assume that our solution is going to be y is equal to x to the m, and then we'll find values for m. So in preparing to solve for this with our assumption, we'll take a couple of derivatives to put back into the original differential equation. And then we'll plug those expressions in to our differential equation. So we have a 2x squared times m minus 1 times x to the m minus 2. We have a 5x times m x to the m minus 1. And then we just have a y, which is x to the m, and all that is set equal to 0. We will notice, of course, that each of the terms will have an x to the m that we can eventually factor out, and that would leave us with 2m times m minus 1 plus 5m plus 1 equal to 0. And then we have a quadratic, 2m squared minus 2m plus 5m plus 1 equal to 0, and then a trinomial that we can solve for by factoring or other means, quadratic formula if need be, but I think this can be factored as 2m plus 1 and m plus 1 equals 0. So that will give us a solution of m equals negative 1/2 and m equals negative 1. So generally, I'd like to put the lesser number value to be our first function. So we have a y1 equals x to the m power, that's negative 1, and y2 will be x to the negative 1/2 power. And just to look ahead, we are y sub c, the whole solution, complementary general solution would be c1 times y1 plus c2 times y2. And this will be the first part of our general solution. Now that we have that, we will use the y1 and the y2 to help us solve for our particular solution. Our particular solution will in fact be of the form u u1 times y1 plus u2 times y2 for the y1 and y2 that's given here, and the u1 and u2 that will be yet to be determined. And this will be based on using variation of parameters. Now, the variation of parameters will require us to actually rewrite our differential equation so that the coefficient function of the first term, the largest order, will be 1, which means we have to divide out by 2x squared all the way across. So if we divide out by 2x squared, we can have y double prime by itself, plus we have 5x divided by 2x squared times y prime, plus 1 divided by 2x squared times y is equal to the right hand side here, x squared minus x divided by 2x squared. Now, in the formulas that we've seen, we often refer to this as your g of x, and then after we can simplify things out, we can refer to this as your f of x. And so, talking about simplifying this out, we can consider this as a 1/2, where the x squareds cancel, and then I have a minus 1/2, and then we have an x times, or x divided by x squared. That will be a 1 over x, but I'll write it as x to the negative 1 because we will be combining this with our fundamental solutions. This is going to be considered our f of x. Okay, now that we've identified our f of x, we can move on to finding our Wronskian and our w1, w2 to help us find our u1 and u2. This u1 and u2 that we're going to find. So we begin with our Wronskian w, and that is going to be collecting our fundamental solution set, x to the negative 1 power, x to the negative 2, or 1/2 power. This will be our first row, and then our second row will be the derivatives of those. So it'll be negative 1 times x to the negative 2 power, and here we get negative 1/2 x to the negative 3/2 power. We want the determinant, so we will multiply x to the negative 1 times 1 negative 1/2 x to the negative 3/2. So we will add the powers 1/2 minus 3/2. 1/2 plus negative 3/2 is negative 5/2. And then going across in the wings, we will get a negative and then a negative sign from here. And there are no constants, but we have x to the negative 2 times x to the negative 1. So we add the powers. Negative 2 plus negative 1/2 is again negative 5/2. So we have a 1 minus 1/2 as the coefficients. So that's going to be positive 1/2 x to the negative 5/2 power. So this is going to be our w, our Wronskian. Now from here, in order to find u1 and u2, we generate a couple of modified Wronskians. The w1 will be the same as the original Wronskian, except the first row will change. So let me first write the second, that's the first column will change. So the second column will remain the same. And the first column will change into the 0 and the f of x that we found earlier. So that's a 1/2 minus 1/2 x to the negative 1. And in finding this derivative or this determinant, we have 0 times that expression. minus 1 half minus 1 half x to the negative 1 times x to the negative 1 half. So that can simplify to be a negative 1 half x to the negative 1 half. Negative, negative is a plus, and then we have a 1 half, and then this will be adding the powers. Negative 1 minus negative 1 plus negative 1 half is negative 3 halves. So we'll have an x to the negative 3 halves power. So we find our W1, and then we move on to our W2, which is going to be the first column of the Wronskian, and then 0 in the f of x. And then here we would multiply the diagonals. X to the negative 1, 1 half minus 1 half x to the negative 1, and then 0 for the other part. And then we'll have 1 half x to the negative 1 minus 1 half x to the negative 2. All right, now we will take each of these and divide it by w. Our u1 prime would be obtained by taking w1 over w, and w1 we found to be a negative 1 half x to the negative 1 half plus 1 half x to the negative 3 halves, and we are dividing that by 1 half x to the negative 5 halves. So I can cancel the 1 halves out, and I will have a negative here. The 1 halves cancel, and then I have x to the negative 1 half minus negative 5 halves. So I'm essentially saying a negative 1 half plus 5 halves. So that would be positive 4 halves, or just squared. It'll be just x squared. And then I will do the same thing here. This is a plus, and then I have a 1 half that would cancel, and then I have x to the negative 3 halves minus negative 5 times x to the negative 5 halves. So we add that or subtract the exponents. 3 halves, negative 3 halves minus negative 5 halves, or negative 3 halves plus 5 halves. So that will be a positive 2 halves. So that's just going to be 1x. All right, so now that's our u1, which is great because that looks like it'll be a fairly easy integral to find. Or this is u1 prime, which means we need to integrate to get u1. Before we do that though, let's identify u2 prime, and that is going to be w2 divided by w. w2 is going to be 1 half x to the negative 1 minus 1 half x to the negative 2, and w we found to be 1 half x to the negative 5 halves. So again, the 1 halves would just cancel, and we have x to the negative 1 divided by x to the negative 5 halves. So we would imagine 5 halves positive minus 1. So that would be 3 halves positive. So it'll be x to the positive 3 halves. And then we have a minus x to the negative 2 divided by x to the negative 5 halves. So we subtract the exponents. 2 minus negative 5 halves. So that's positive 5 halves minus 2. Or positive 5 halves minus 4 halves, so that's just going to be 1/2 positive. So from here, we would integrate to find u1, and that would just be the integral of, let's rewrite this as x minus x squared dx. Looks like a fairly easy integral. This is going to be 1/2 x squared minus 1/3 x cubed. And we can ignore the plus c, because if we multiply the plus c with y1, and that would just be kind of merged with the c1. So we'll put the plus c here, but then we'll not worry about it when we put it in our final form. Our u2 will be equal to the integral of x to the 3 halves minus x to the 1/2, and that will yield adding 1 to the power, so that's going to be 5 halves, and it will divide by 5 halves, which is the same thing as multiplying by the reciprocal 2/5, minus x to the 3 halves and multiplied by 2/3. Now it looks like none of these will match each other, so I think we're ready to put together our y sub p. Y sub p, as noted, was u1. That's a 1/2 x squared minus 1/3 x to the 3rd times y1, and y1 I believe was x to the -1 power. And then we will add u2, which is 2/5 x to the 5 halves minus 2/3 x to the 3 halves, and that we are multiplying by x to the -1/2 power. So some simplifying might be worth the time to see if we can combine things. Here we're just going to subtract the x, or add the exponents, 2 minus 1, or 2 plus -1, so that's going to be 1. We have 1/2 x to the 1st power minus 1/3 x squared, plus we have 2/5, and then here we have x to the 5 halves minus 1, so minus 1/2. So 5 halves minus 1/2 is 4 halves. I think that's squared again, minus, and then here 2/3 x to the 3 halves minus 1/2. That's just going to be x to the 1st power. Oh, it looks like we can actually combine them. We have some like terms here. Unfortunately, the denominators aren't agreeing with each other, but let's see if we can do this. Let's put together the x squared terms first. This is 5 halves and minus 1/3, so let's call the common denominator 15. So with a common denominator of 15, this is going to be 6 minus 5, which is just going to be 1. Alright, so that takes care of the squared terms. Now the x term, I don't know if it's going to be a plus and minus, so we'll just say this is an x. This is a 1/2 minus 2/3, so the common denominator is 6. This will be 4, -4, and this is positive 3. So that's going to be -1 with a common denominator 6, -1/6 x. So that is your other term, and now we've simplified this. And if you look at the original function, the g of x function, it had an x squared minus x term, so it kind of makes sense that we have an x squared and an x term. Okay, our final answer. Y will equal to C1 times the Y1 value that we got, plus C2 times the Y2 function, plus these other two terms that we got as a Y sub p. So this is 1 over 15 x squared minus 1/6 x. that is your final answer. Okay, I hope that helps, and good luck.